Welcome back. Good morning. Quick announcement before we get started. Today's Friday. Congratulations. You made it through the first week. This afternoon, we'll have a bit of a special series. After lunch at 1 o'clock, Abe will be back and will give us a little bit of background and history on the center here at Stony Brook. And it's good to have him. He's off to Japan next week, so this is our last chance to interact with him. And then in the afternoon, we'll have the student flash talks. And so the first set of flash talks is filled. They are on Indigo with your email address. So if you go into Indigo, you can use your email address to make an account, upload your talks, change your name. Any problems, let me know. If you can't upload them, please send them to me during the first session, and I will upload them myself. If you send them during the flash talks, I'll be busy during the flash talks, so I can't do that. We have a few slots left for next Friday's flash talks. So if you would put those up, because I'll post those shortly. And I think we're ready. Anything else, or?
I don't think these slides have been uploaded yet.
I will upload afterwards because I'll have a couple of exercises for you today.
There are surprises there.
There are surprises, yes. So that,
Having said that, it's Friday. So the first week will be over, and very soon. Our first lecture is the second lecture by Pavel.
Okay, well, thank you. So we'll continue talking about unpolarized PDFs, and today I would like to kind of establish a better connection to what we will do with unpolarized PDFs at the Electron-Ion Collider. And the first thing I would like to point out that you already probably heard, some details about the program of various measurements that can be done at the EIC. And so, well, this is a nice chart summarizes that. Various kinds of studies that can be done, not just at the EIC, but potentially at other colliders like LHEC or the EIC China. It's a function of the center of mass energy that can be reached and the luminosity, right? And so then, of course, initially, both the energy and luminosity are relatively low, but as the program goes on, so you will be the measurements will be more and more detailed, and you can start by checking some, let's say, for evidence of new phenomena like saturation. But as time goes by, the measurements will become more and more precise. And roughly speaking, let's say towards the end of the EIC runs, the precision will be high enough, and so we will have to deal with a variety of issues that we are currently trying to address in the context of the LHC physics. So at the LHC right now, we entered into the stage of precision QCD. And so I will emphasize today some issues that arise when the precision goes up, right? So for the discovery, these issues may be less important, but let's say that after a few years of running of the EIC, it accumulated lots of events, and you have to analyze them. And for that, you need to have precise predictions. So then whatever you do at the EIC, somehow you will need to have unpolarized cross-sections as a reference. And to calculate the unpolarized cross-sections in a typical setup, you will need unpolarized PDFs. And of course, whatever you learn about unpolarized PDFs can also be translated to many other measurements, let's say about the spin PDFs or the nuclear PDFs. Okay, so that's kind of the path that can be foreseen. And then, so just to remind you where we stopped last time, I started talking about global fits of PDFs that in the unpolarized case now are done at the NNLO. This means 3-loop order in alpha-S. In some parts already at N3 LO accuracy. So these are very precise analysis, probably the most precise in modern quantum chromodynamics. And I talked a little bit about, the CT25 analysis, which is one of the analyses that, is available. I'll briefly mention the analysis by other groups. And so today I would like to talk a little bit more about this procedure of the global fit. And then we'll try to do some exercises. Also would like to give you an idea about some issues that we have to deal with. And so one thing that I emphasize is that on one hand, we determine the most precise PDFs using a very large number of experiments of very different kinds with very different systematic effects. And they are very precise, but this also means that they are sensitive to many factors. And so somehow, whenever we try to extract information from these experiments, we need to balance between precision and complexity. Or precision, well, that related concept is replicability of measurements, because if, at some point, if the measurement becomes too precise, this means you have to control for many factors, and your results do not reach the nominal precision simply because there are too many things that affect your measurements. Okay, and so that's kind of one issue that you have to address. So I mentioned to you that in our feeds right now we have about, let's say, 4,000 data points, but we also have many parameters that describe, on one hand, pattern distribution functions, but also they describe various systematic factors in the measurements. And so if you take, let's see, our recent analysis, for 4,000 data points, we have about 2,000 factors describing systematic effects. And those are behaving like so-called free, nuisance parameters. So they are really like free parameters that are added to the analysis. And one big challenge is to understand how to treat the systematic factors, right? So because they will propagate into the uncertainties. And so therefore, the whole pipeline that for the analysis is indicated by this chart. So on one hand, we get the most precise data that is available. We need to compare it against the most precise theory, but then these analyses are very complex, and we need to use very advanced statistical methods. So this is the triad that we have to address. And each of these three areas is important in the analysis, right? And so you could be an experimentalist who understands well the measurement. You have to be, but you also theorists must put their effort, and so they need to be able to provide correct and numerically efficient calculations. But then there is another big part that becomes increasingly important in this era, and this is the statistics. And so I'll try to kind of briefly mention to you all three components, how they work. Okay. Now, if we talk about the EIC, so there is another interesting connection, which is the following. So basically, the EIC will study the three-dimensional structure of hadrons. And what this means on one hand, we'll have precise measurements that, like, for example, we could in principle use the most precise calculations that are done in QCD that we use to determine the PDFs. But then we will also have non-perturbative models of the same, let's say, non-perturbative functions. And they will come from lattice QCD or from some other models. And then somehow you need to establish a connection. So let's say we would like to learn something about nuclear theory. You need to know how exactly, you test these non-perturbative models using the formalisms that are developed more like for let's say, perturbative QCD. Okay, so there is a connection. So you need to validate your predictions. And basically, that's kind of a prerequisite for any kind of precision test that you are going to do at the EIC, but also, of course, at other facilities that probe similar issues. And then if you think a little bit about it, so actually, this is a very, very subtle breach, right? Because let's think about it. So let's say we see that the typical energies of water 1 GeV squared. Well, the processes at these energies are still relatively simple. And so they are dominated by non-perturbative dynamics, right? And so, like, for example, if you look at hadron production at JLab, well, in each scattering event, you only produce a few final state particles. Now, if you go to very high energy, let's say the LHC, so the picture of the events is very different. So you have lots of energy coming in. You produce showers of particles that can be described by perturbative dynamics. While for the intermediate energies, non-perturbative effects are important. Okay, and so when you say I measure the pattern distribution function, well, at the EIC, you kind of sit at this transition region where you go just from these three constituent quarks to the picture in terms of weakly interacting quarks and gluons. And so the big question is that how do you relate these two regimes, right? So therefore, that's again will be the challenge. You can measure something in the EIC, apply your pattern showers, but do the pattern showers really match on something that you can calculate, for example, on lattice QCT using this simplified picture that is relevant at low energies? Okay, so then that's kind of a big question that will emerge. Okay, so therefore, what I believe it will, if you work in this area, as you move forward, you will find more and more questions about how to do things properly, right? And so I just listed a few questions that arise. It should be frequent questions from users of PDFs. And again, so we can discuss some of them during the barbecue, right? But okay, so one typical question will be, so if I really compare my low energy PDF calculation, does its definition match on the PDFs that I extract from the data, right? So what is the definition of my PDF? How important are high order contributions from QCD? What is the right way to estimate the PDF uncertainty? So I will emphasize today that there are many ways to do that, right? So what to do about the parameterization of PDFs? So the PDFs, well, we don't know their functional form, right? So really, well, one way you can think about it is kind of PDF is kind of like a similar to neural networks. So there is some kind of a function which in principle can be arbitrarily flexible. It has infinitely many degrees of freedom, but you cannot constrain infinitely many degrees of freedom with a finite amount of data, right? So then how do you constrain the class of the pattern distribution functions that is acceptable for your analysis, right? Well, many other questions like this, right? And so then again, you probably already read the rest. So again, so these questions are kind of universal. So if you understand them on the case of unpolarized PDFs, your life will be much easier when you encounter these questions for any other kind of non-perturbative function. Okay, so obviously, in the short time, I don't have, well, I am not able to cover all these important questions. And what I would like to point out is that please think about it if this is interesting to you. But if you would like to learn more, there are very nice references that are written in the past years that contain lots of information. And you know, if you have, you would like to kind of dive in depth into some of this, you can take any of these reviews. So there was a paper prepared a few years ago for the SNOMAS study that summarizes recent trends in the global analysis of proton PDFs, and it is a collective work with about 30 experts on pattern distribution functions that will also provide you various viewpoints about how you can think about these issues. And for some of these questions, well, there are several viewpoints that somehow, well, may not necessarily be perfectly identical to each other, right? So then there are textbooks on QCD, and so one of them that discusses, well, at least some of the issues that I will cover, it's called the Black Book of Quantum Chromodynamics. You see, I cannot share the slides yet because I still have typos, right? So it's the Black Book of Quantum Chromodynamics. It is written for the LHC physics, but many insights are also applicable to the EIC, right? So for example, there is a nice chapter about the determinations of unpolarized PDFs in this textbook. Okay, and by the way, again, so ask me questions. So raise me your hand if you would like to, maybe need to slow down. Okay, so now let's a little bit talk about this NNLO and partial N3 law PDFs. And so I mentioned to you that there are many ways to produce them, but fundamentally, if you actually summarize what the global analysis does, so the full problem of the global analysis can be written within one slide, okay? And so what we really do, and I can come back to this slide as we go along. So we try to solve a so-called inverse problem. So how many of you know what inverse problems are? Okay, some of you know. So what is the inverse problem? Can you give us a kind of a general statement? What does the inverse problem do? maybe in the back there.
We try to reconstruct a continuous function from a finite set of points, but you have a linear operator in between, so you have to convert that operator, but it's not well defined.
Yeah, so basically, I think you said it very well. So the inverse problem, it's a typical problem that arises in what is called inference of something from measured discrete data. So you have a discrete data which has, let's say, I don't know, NPT points, but you would like to find something that in principle can depend on more degrees of freedom than just at these NPT points. Continuous functions in principle, they have an infinite number of degrees of freedom, right? And so again, we can discuss how this works, but basically you try to make some guess about this very kind of large number of degrees of freedom, and you would like to solve this problem in a sort of well-defined way. And so again, there is a lot of thoughts going on in how to solve this problem. So there are well-defined inverse problems. They satisfy so-called Hadamard's conditions, and not so well-defined. Okay, but ultimately, what you will do is that in this case, you will do a probabilistic judgment. And so again, if you read carefully here what is written here, so really we are trying to do the Bayesian analysis, and we try to make an estimate about these continuous functions by solving the bias theorem. Basically, we have evidence for certain theories, models describing data. So this is so this is called the likelihood probability. And knowing the likelihood probability and some prior assumptions about these continuous functions, we would like to essentially rank our models in terms of their the probability, and that's what gives us the solutions for most probable models of PDFs. Okay, and so then literally this slide shows the two paths that we can follow. And so, okay, so now let me try to explain to you maybe, one place that, I kind of go through this step by step. But one point that I would like to emphasize is that there are two methods for solving this problem. One, which is actually shown on the right-hand side, it's a classical method. It's a method of maximal likelihood, actually maximal posterior probability in this case. And that's what we do within the CTEC analysis. And so when you say you feed the PDFs, what you do, you solve this inverse problem using the maximum likelihood method. So then the other method is the Monte Carlo method. And so the Monte Carlo method, it works especially well with universal approximators like polynomials or neural networks. And so these two methods, are very commonly used in the global analysis. And then now that's basically what the various groups do. And so then, this slide shows the progression of various kinds of analysis as a function of time, right? And so what I would like to emphasize, here you have the years, right? So right now we're in 2025. And so I already mentioned our CT25 analysis that comes out. But you see there are many other analyses from other groups, ABM, Atlas. So there are two major groups, MSHT and NPDF, working on a precision unpolarized PDFs. Then there is CTEC JLab, GEM. So they're more interested in low energy effects. Like GEM, for example, also simultaneously feeds PDFs and fragmentation functions. And so you see there are many analyses that are available. Obviously, I don't have time to discuss all of them, but maybe a little bit to give you some ideas why we need so many analyses. Well, one reason is that you can have PDFs. It's kind of like a Swiss Army knife. So you would like to have what is called the general purpose PDF that kind of works okay on average, right? It can do many things. People experimentalists will use it for all kinds of simulations. And so these general purpose PDFs are the most difficult to produce because they have to be performing reasonably well in all sorts of situations. And so the CT25 analysis, the default one, falls into this category of the general purpose PDF. And now then there are two other analyses which are recent, MSHT20 and NPDF 4.0. And so these numbers change as the new versions of these PDFs come out. But then there are specialized PDFs. So whenever we produce this general purpose, we also have additional sets that serve a slightly different purpose. Like, for example, when we release CT25, we will release several other sets with the different maximal number of flavors, PDF set NLO and leading order. So then you can select data differently. So I can show you what the selection of the data does. You can do the statistical analysis differently, right? And then, okay, so you can do PDFs with the fitted charm. By default, we just generate the charm perturbatively. We only have the extrinsic charm in our analysis. You can include the photon PDF. And finally, so there is another important set of PDFs which tries to combine PDFs from several groups into a single set. That kind of works on average for the majority of situations. And it sort of averages over the differences among the inputs, okay? And so then you basically need to decide which PDF set you are going to use. Well, it can be quite important. For example, let's look at this plot. So what this plot shows, you already saw it in the first plot figure. It shows the PDFs for various flavors plotted in such a way that we emphasize their behavior at very large X values, which will be relevant for the EIC physics. And so so I showed you the plot for the full CT25 data set. And what I mentioned to you is that one of the challenges for our upcoming measurements is to do quark C flavor separation. Okay, and so then now I mentioned to you that right now we believe that there is more T-bar antiquarks than U-bar antiquarks at large X. But this is based on including the deuteron data. Okay, so therefore the uncertainties that you saw in the past lectures, so they reflect the impact of the deuteron data, which may have a deuteron binding correction, right? So therefore one interesting question is what happens if you remove nuclear data sets from the analysis? Well, we have two kinds of nuclear data sets that go into the default CT25 fit. So we have the heavy nucleus correction, like from iron or copper, and they are especially important for constraining the strangeness. For example, there is a measurement, the Newton measurement, that constrains the strangeness PDF at very large X values, but it is done on the nuclear target. And so there is some mismatch between the measurement of the strangeness that is done by the Newton measurement versus what you see in the measurement of strangeness at the LHC. Okay, so then one question would be, suppose we take out this heavy nucleus data, what does it do to the PDFs? And so the answer is that it actually increases the size of the strangeness uncertainty quite a bit in the large X region. Right, and so it can be more. In principle, there can be some kind of solutions, like almost like the intrinsic strange. So you can have more strange quark PDF in some region that are U-bar or D-bar, right? So that's one effect. So now this middle one has both the proton and deuteron data sets inside of it. But we can go even further, and we can create a so-called CT25. I guess in this case it will be flat P and then a low envelope, where we also remove the bias due to the deuteron data. And so in that case, what you see is that their ability to resolve this PDF, the CPDFs at large X is completely washed out, right? And so that may be good for the EIC, because the EIC may come in and say, I do not want to be biased by the deuteron correction. Let me come up with some measurement, let's say semi-inclusive TAS. And let me try to resolve this degeneracy. So then you will use this proton-only data set, PDF set, and not the default CT25 data set. And so that's why we provide this PDF set, the proton-only, which nominally is less precise, but it's also less biased for whatever new measurements you would like to do. Okay, so is it clear? So, right. So what's going on here? Okay. All right. So then now the other maybe is that I would like to put in is that we would like to put in higher and higher orders of corrections in the analysis. And so recently you may have heard about so-called approximate N3 law PDFs, which, okay, so now you may think that they will be definitely better than NLO PDFs because they include some part of the high order correction. right? And so there are two groups that release this approximate N3 PDF. Well, you have to be careful though, because what happens in this QCD calculations, well, each QCD calculation guarantees perturbative convergence, right? So basically, whenever you put all inputs of a given in a given order of alpha S, if everything is done correctly so that this all inputs will match, and so the accuracy will be automatically, or let's say uncertainty will be automatically a high order compared to, well, the full order of your calculation. But really, the important thing here is that you really need to put all relevant pieces of the same order in alpha S together. And so this has not been done. Okay, so the analogy that you can think about it, each perturbative QCD calculation, it works like a precision clock, right? Like a Swiss watch, right? And so now, well, if you have a Swiss watch, you have a guaranteed certified precision. You cannot have an approximately precise Swiss watch, right? So the Swiss watch is either precise or it's not Swiss watch, right? And it's a little bit of a situation here. Now, of course, it's very difficult to put the whole N3 law calculation to the analysis, right? But right now, this analysis, well, they're kind of like this approximately precise Swiss watches, right? So it's sort of, well, okay, you can buy an approximately precise Swiss watch, but I don't know if that's the best, investment of your money. Okay, but nonetheless, okay, so people are working on this and they do all kinds of calculations that will be needed to put in. And again, I can come back to this. So basically, right now, there is a lot of effort going into trying to get this Swiss watch, well, close to the certified precision, if you like, right? Which is a major effort. It requires work of multiple people. Like our group works on including these N3 law contributions in our fitting codes. There are already some of these published, partial N3 law fits. But what you have to keep in mind that certified N3 law accuracy is still a few years in the future. It depends on calculating all the most important pieces from these various processes to the N3 law accuracy. Okay. Okay, so then let's talk a little bit about what requirements for PDF parameterizations are. And something that maybe the first thing I would like to point out is that, well, I mentioned to you that in principle PDFs, well, they are infinitely dimensional functions, but they are not completely arbitrary. And so there are various requirements that we impose on these PDFs. Now, the first requirement is that they must satisfy so-called QCD sum rules. Right? For example, I don't know, have you heard about this QCD sum rules before? Yeah, let's say, for example, suppose we take the U and U bar PDFs, right? So if you take the difference, U minus U bar, so this is called the non-singlet minus, or it's called in the kind of simple parlor, it's called the valence U quark PDF. And so there are two constitute U quarks in the proton. So therefore, the integral of U minus U bar over all momentum fractions must be equal to 2, right? So whatever we do to this parameterization, so we must have this integral, the valence quark, U valence quark sum rule equal to 2, right? So then for D quarks, the same integral must be equal to 1, right? And for strangeness, well, because there is no total strangeness quantum number in the proton, the difference S minus S bar must be equal to 0. Okay, so the difference for C minus C bar must also be equal to 0, right? So therefore, the S can actually have a different shape from S bar, but the integral must be imposed at all times, and that's actually can be quite tricky to implement in the parameterization. Okay, so then there is another sum rule which is called the momentum sum rule, which tells you that if you now multiply all PDFs by the momentum fraction, and then you sum over flavors and you integrate the momentum fraction from 0 to 1. So you get the total momentum fraction of the proton, which is equal to 1. Okay, so that's the momentum sum rule that constrains the gluon PDF if we know the quark PDFs quite well. Okay, now then the other important requirement is that a valid PDF set must not produce unphysical predictions or anything that can be observed. And what I mean by this is that, for example, the PDF I mentioned to you in principle can be negative, right? So there is no so-called positivity requirement on the PDF, but the cross sections cannot be negative. So the cross sections are probabilities. So therefore, if you do a calculation, if you find your PDF produces a negative cross section, well, that's bad, right? So because in principle, there may be some conceivable measurement that will test the sign of this cross section, and they will rule out this PDF. Somehow you have to impose this positivity of cross sections as a condition on the PDFs. And it's not straightforward because cross sections are not just proportional to the PDFs, they involve convolutions of PDFs with hard cross sections, okay? So similarly, any kind of the asymmetry, if the asymmetry can be, physical asymmetry can be between -1 and 1, so the cross sections must produce asymmetries that lie between -1 and 1. And so again, there are recent examples that you can find it is that there are some PDF parameterizations that may be nominally outside of this range within the uncertainty, but then you know that again, so maybe you need to do some adjustment to bring in these PDFs into this range. Okay, all right. So then, then let's talk a little bit about this question about flexibility of the PDF, right? So then we are solving the inverse problem, and in principle, the PDF can wiggle very quickly. So you can have an ultraviolet catastrophe for the PDF parameterization, right? So you can have very short wavelengths contribution, but the PDFs cannot be that. So somehow you need to make a decision that the PDFs must be flexible enough to describe the data, and they must satisfy these various conditions like positivity, sum rules, but without reproducing random fluctuations. Okay, and so that's kind of, okay, so a typical problem that you will encounter in particular in machine learning, right? So you must come up with some parameterization of the function that is not overfitted. In this parallel, well, and you can ask again, what do you mean by overfitting, right? So, but that's sort of the rough intuition that you have to address here. Okay, so then how do you find this kind of parameterizations? Well, one way you can see it is that I just take a theoretically motivated function, right? So for example, a traditional parameterization will tell you that I always write my PDF as a product of two functions. One is given explicitly, and that's actually was initially this was just the full parameterization of the PDF, and this first function is based on the asymptotic behavior of the PDFs in the limit when x goes to 0, when you can apply so-called Reggie-like model to describe the PDF behavior that tells you that the PDF must grow like x to some power a1. Okay, so that's one limit. And the other limit is when x goes to 1. And again, there is a very nice physical consideration that the PDF must fall off when x goes to 1 as some power of 1 minus x. So therefore, okay, so you must have these two terms to realize the asymptotic limits. What happens in between, you don't know. And so here you put in some kind of universal function, and ideally you can have a universal approximator function that can take any form. Okay, and so then in the old days, you will just use polynomials as universal approximators. Even now, you can use polynomials as universal approximators, but something that was realized in the 19th century that polynomials of sufficiently high order can approximate any function. Okay, so basically what happens is that that's me. Yeah, what happens is that nowadays we use neural networks to approximate functions, but polynomials will do a good job for these one-dimensional functions as well. So you just need to properly construct these polynomials, and there are very well-known examples, and I'm sure that most of you use polynomial universal approximators somewhere in your work. So basically, you can approximate this intermediate behavior by a polynomial. Now, you can use the neural network as well, and that's actually another choice that you can make. So then if you do the neural network, you need somehow to impose some rigidity condition. And so something that I probably will skip, but basically the big idea here is that you do resampling and bootstrapping and cross-validation. Okay, and so the idea, for example, would be that you generate replicas of your data by random fluctuations. And so then you fit half of the data set, or let's say 70%. And then what you do is that you divide, these replicas into, okay, so basically you require that on one hand, your fit gives you the, the good description of the old data, but or the fitted data, but then you also require that you do not get a bad chi-squared for the cross-validating data or the testing data, right? And so that somehow reduces the flexibility of the neural network. Okay. Okay. So therefore, what you see is that basically there are two approaches, right, to parameterize PDFs. One is the traditional approach, and that's what we use within CTech. And so this approach, well, again, so skipping details, you can describe it in terms of the information theory as Bayesian exploration with Gaussian emulation at the end. Okay, and so the other word that you can apply to this, it uses a technique called proper orthogonal decomposition. Now, this is a technique that becomes increasingly popular, but basically this CTech-like fits, they will use this kind of traditional approach. And then there is another approach based on neural networks. Okay, and so I have two slides and I can go through them in detail. So let me talk about the neural networks. For example, the neural network PDF ensemble is generated by using a neural network to approximate this interpolating functions. And okay, so now what they do is that they bootstrap the data. And let me make clear again what I mean by this. So what they do is that they create, let's say, 1,000 replicas of the data that are exactly the same in all aspects, except their central values are fluctuated according to the statistical errors provided by the data. And so then they feed these fluctuated data sets using a neural network, using cross-validation for each of the replica. And so then they get a set of 1,000 solutions, which differ only in these random fluctuations. And so these random fluctuations, they go by another name. It's called aleatory fluctuations. Aleatory means dicey fluctuation or aleatoric. So basically what the neural network does, it estimates the aleatoric uncertainty in this case. And that's kind of naturally comes out from this bootstrapping and resampling. Okay. Right. Okay. So then now it turns out, however, there are other kinds of uncertainties. And maybe that's what I would like to emphasize is that, well, this aleatoric uncertainty due to random fluctuations is not the only one that contributes. And you can also have another important class of uncertainty, which is called the epistemic uncertainty. And how many of you have heard it actually before? Aleatoric uncertainty versus epistemic. Have you heard it before? Okay, so then let me explain what it is. Before I go there, let me explain why this is important. It is important because actually this epistemic uncertainty, which is more difficult to estimate, results in differences in the uncertainty estimates coming out from various PDF sets. So there is a so-called tolerance puzzle, which means the following, that I mentioned to you a variety of measured PDF determinations that were produced. But the PDF determinations don't agree within the stated uncertainties, at least in some cases, which means that the uncertainties are misestimated somehow in some cases. And so the question is why? Well, one possibility is that we have different definitions of the uncertainties. And that has implications for all sorts of things. For example, you could make predictions for Higgs production cross-sections, and you can fit more or less the same data sets, but you can come up with different uncertainty estimates, even if the procedures are very similar. And so this can have all kinds of high-stake implications, right? So if you would like to rule out the hypothesis, you need to know what the uncertainty is. If you don't have a control of uncertainty, so you can come, well, basically you don't know what to do with this data, right? So because it leads to inconclusive results. Okay, so then very quickly, so where does this aleatoric epistemic distinction comes from? Well, it comes from information theory. And so basically, whenever you think about the uncertainties, you can classify them in two ways. One would be what is called the domain classification related to your own subject. And these domain classifications are very well established. In the case of PDFs, you can have uncertainties coming from the experimental side, theoretical side. Then there are two classes of uncertainties. One will be related to parameterization, right? And so it's how you parameterize the PDF. And this is an important source of uncertainty. It can contribute at least 50% of the stated uncertainty, let's say in the CT25 analysis. So the other class is called so-called methodological uncertainties. And so this is related to any procedure that you choose to do in the fit. For example, if you select a particular subset of data, right? So this will be part of your method, right? And so these uncertainties are also important. So now these two uncertainties, they are a part of the epistemic uncertainty. And so the epistemic versus aleatory comes from information theory classification. So basically, now information theory doesn't care about the domain aspects, right? It simply think about fitting the data, but then they will classify uncertainty in two kinds. One will be aleatory or dicey or random, and this can be any kind of statistical fluctuations in the data. And the other is the epistemic. And so those other class, epistemic is related to the choice of the model. Okay, so epistemic uncertainty cannot be beaten down simply by using more precise data. It simply reflects, how good your model is, or what class of model is available, because you can also think about sampling of various distributions. Okay, so then, all right, so then I have a, here you are. So I have a slide explaining what kind of considerations go into this epistemic uncertainties, and I will skip it for now. But one thing I would like to point out that it is important for various analysis, but also it's actually quite difficult to estimate it. In the difficulty with inverse problem primarily lies with these epistemic uncertainties. Well, here's one reason why. That whenever you have many parameters, so the statistics with many parameters works quite differently from the textbook statistics with a few parameters that you study in a typical introductory course, right? And epistemic uncertainty will be related to the fact that you have many degrees of freedom. Okay, and so this is, again, so this probably should take another lecture, but maybe here is one exercise that I would like to emphasize is that the geometry of multidimensional probability distributions is different from what you naively think. There can be violations of kind of basic results in the statistics. For example, if you apply the central limit theorem all the time, you will find that in some important cases, you will make a mistake with multidimensional probability distributions. And the reason is that the central limit theorem works when the number of points greatly exceeds the number of parameters. If you have the number of parameters that is comparable to the number of points, the central limit theorem does not work. Okay, and similarly, if you sample these multidimensional probability distributions, you can also run into an issue that basically, well, you will have an inefficient sampling. So it's very difficult to sample the full probability distributions. Now, I'm going a little bit slow. Okay, but I would like to give you one exercise. Okay, so here is just to this point about geometry of these distributions. So look at this chart. So the chart showed something that there is one parameter on the horizontal axis and something else is plotted on the vertical axis. And so these are the values this function takes at the parameter x parameter equal 1 pi 4 pi over 3. I'm sorry. So the for parameters 1, 2. So the values of this function for parameters 1, x equal 1, 2, 3, and 4 are equal to 2 pi 4 pi over 3 and 528. Okay. So then what is this function? What I am plotting here? So can you have a guess? So basically, I give you the values of this function for the values of the parameter equal to 1, 2, 3, and 4. And so these are the values. But then what does this function represent? What property or what object has the property described by this function? And what is that property? Any thoughts? Anyone? So what are your hypotheses? So think about these numbers. So what can these numbers mean? For example, what is 4 pi over 3? So what can have the value of 4 pi over 3 for the parameter equal to 3? Yeah.
My first thought has to do with volume.
Volume of what?
And spheres.
N spheres. So these are volumes of N spheres.
Unit ends not. Yeah, it might be units of volume. Volume of unit N spheres. I think the one-dimensional sphere might be 2.
Yeah.
Radius 1.
Right. So basically, these are volumes of a unit, what is called a unit ball in N dimensions. So here I put plot dimensionality, and here I plot the volume of a unit ball, right? And now what you see is, okay, so basically, here's a formula that shows that. And now you see something very interesting, that the volume of a unit ball grows up to about 6 or 7 dimensions, and then starts dropping like crazy. And like, for example, now to estimate the PDF uncertainties, I need to know the size of a unit ball in, let's say, 28 dimensions. Well, the size of this unit ball, the volume will be something like 10 to the negative 4. Okay? So, and that's a reflection of this geometry, and this is kind of leads to the phenomenon called the curse of dimensionality. Well, for example, it is very difficult to estimate uncertainties with many dimensions, but also any kind of sampling will be affected by this kind of effects. Well, I'll give you an example. Let's say, well, again, so this is a picture. Let's suppose we would like to do the analysis in 2 dimensions, and suppose we would like to find an inscribed circle that contains, let's say, 68% or 80% of probability in 2 dimensions. Well, and you have some kind of region that is given by a hypercube. Well, you know if that the diameter of the inscribed circle is equal to the side of the hypercube, then most of the volume in these 2 dimensions will fall inside this circle. So they're like, for example, the area inside this circle, and that's, let's say, this is an area of our interest, will contain about 80% of the area of the whole square that contains it, right? So therefore, like if you were to randomly sample, try to hit the inside of the circle, you drop the pins inside the cube, and 80% of time you will hit the circle. Well, if you do it in 25 dimensions, you will have essentially no probability to hit the unit circle, because most of the volume sits in the corners of the cube. And by the way, in this case, the cube is still called a ball, according to so-called L infinity norm, right? So basically, but the most of the volume sits very far away from the center, and this has an implications. Like, for example, let's talk about probability distributions. Well, again, if we talk about one-dimensional Gaussian probability distribution, suppose we kind of try to randomly sample it. So if we know for the one-dimensional Gaussian, 68% of the pins will fall in the interval of the parameter between -1 and 1, right? So basically, if you simply randomly drop the pins, well, according to this Gaussian distribution, so 68% of them will fall within 1 standard deviation. If you try to do the same in many dimensions, for example, if you try to sample the 25-dimensional probability distribution, well, most of the pin will fall far away. And so most of the pins will follow, at the distance which is equal to the square root of the number of dimensions, right? So let's say you would like to sample your PDFs using the Monte Carlo sampling while using the, let's say, the resampled data. Well, most of the feeds to the resampled data will be very bad feeds to the central, to the published data because of this effect, because most of those replicas, or 1,000 replicas, will be square root of the number of parameters away from the best fit. Okay, so therefore, with this Monte Carlo sampling methods, you kind of run into a conundrum that you can have very flexible sampling, but you run into the situations like this where the feeds to the resampled data are bad feeds for the actual published data. And so then, now, of course, what you also will realize is that, if you average, you calculate the averages for these bad replicas, you will still have a very good estimate where the average of this whole sample is. But each individual replica of the fit will be a bad fit. Okay, so you cannot take, for example, NNPTF replicas and they say they are good fits. They are not good fits for your central data. So only the average of these replicas are. Okay. All right. So that's the point, and that's the point that emerges all the time when we work with the epistemic uncertainty. So then, now I'm completely out of time. Have too many slides, and so then I will keep going. So then very quickly, what you can do with the with the uncertainties. And first of all, how do you estimate the uncertainties? Well, let me very quickly explain the traditional way to estimate the uncertainties. Well, it's based on the mean chi-squared, right? So here I plot the chi-squared as a function of one parameter. And typically what we do is that we calculate the minimum of the log likelihood, and log likelihood, we call it chi-squared. And the minimum, we say, corresponds to the most likely value of our parameters according to the data. So then there is a whole question how we estimate the uncertainty around it. And so there is a standard prescription saying that if basically deviations of data from your predictions are purely random, so then the 68% uncertainty interval for this parameter is given by the increased delta chi-squared equal 1. Okay, so basically we have a prescription how to estimate the uncertainty on this parameter. And so this estimate will tell you that regardless of how many parameters you have, if you have just one parameter and you have purely statistical fluctuations, well, the region corresponding to the increase of chi-squared by 1 unit contains 68% of your values for this parameter. Okay, so that's a very classical result, and you need to remember that it works in many cases. It does not work in some practical cases, and basically what you have to be careful is that you always ask, well, first of all, is my distribution Gaussian, right? So, for example, you could have something like a landscape, where a very famous example is so-called string landscape. So you may have not just one global minimum, but you have a kind of landscape of many minima and maxima, and you may be stuck in one minimum, local minimum, but there is no single local minimum. And for example, if you have many measurements that don't disagree, so you will have not one minimum, but you will have many minima, and you don't know which one to choose. So the number of the minima grows factorially with the number of disagreeing experiments, just like in the case of the string landscape. So if you have lots of disagreeing experiments, you may be in a situation of this very bad landscape, okay? So that's one thing. So the other thing, the situation that you also have to be worried about is flat directions. So you could have parameter combinations that are completely unconstrained by the data. And so then you cannot estimate the uncertainty along these parameter directions. And so somehow your analysis must be smart enough to avoid the situation. Now, what fortunately happens is that actually we are not in those pathological situations. So we typically have a chi-squared function that actually has a pretty well-pronounced global minimum, except it's not purely Gaussian. It will be, let's say there is a well after the chi-squared function, but this well is not perfectly Gaussian. It has some kind of structure, right? And so then the question is, how do you estimate the uncertainty? Well, because this kind of works almost like Gaussian. You could come up with some approximations. For example, you say, well, one thing that you could do is that you could see how this chi-square function varies when we change the assumptions. So then you don't have just one outcome of the fit. You have a set of outcomes. And then you can come up with an effective Gaussian approximation that on average captures the shape according to the ensemble of the replicas. And so that's what is called the Gaussian emulation. Okay, so you have many solutions, but you write a Gaussian emulation that on average reproduces the likelihood according to all the solutions. And then this Gaussian approximation results in a parabola that is generally wider than the parabola corresponding to delta chi-squared equal 1, because it contains additional pieces of information. So you need to decide on the width of this parabola. Okay, and so then you can come up with a tolerance, a so-called tolerance criterion, which says that my 68% probability is contained not in the interval delta chi-squared equal 1, but delta chi-squared equal to t squared, where t squared is larger than 1. Okay, and so this is a kind of a simple prescription, which is called the global tolerance prescription. Okay, so then there are other prescriptions, like, for example, you say, let's not work with this global tolerance, but you could do Monte Carlo sampling, and I'll skip this. And so you basically, Monte Carlo sampling will have its own issues. I already mentioned to you some of them. So basically, Monte Carlo sampling is difficult in the case of many dimensions. Okay, but this Hessian formalism is quite powerful. And maybe in the last 5 to 10 minutes, I'll show you one technique that to show how this Hessian formalism works. For example, I asked you a question yesterday. Suppose I'm giving you some cross section, and okay. So how do we know which PDF flavor and in which X range dominates the PDF uncertainty in this cross section? Okay, and so I don't know. Did anyone think about it? Does anyone have an answer to this? So if okay, so you need to decide, like for example, you would like to make a prediction. You made a prediction for the AIC, but you know there is some PDF uncertainty that comes in, and you would like to propose a new measurement or another set of measurement that will reduce this uncertainty. So what techniques could you use for that? Anyone ever encountered this kind of situation? Thoughts? Okay, so I'll give an answer since we're out of time, right? So basically, one way you can do this is that you can use this Hessian formula to estimate, well, essentially like correlations between the PDF uncertainty for your parameter, for your measurement of interest, and any other measurement that determines PDFs, right? And so basically, well, again, this is basically a formula which is based on so-called Hessian correlations and sensitivities. And so these correlations and sensitivities can be easily calculated if I give you either Hessian or Monte Carlo error PDFs. For example, you could take CT25 error set, right? And so then you also need to know the chi-squared values for your fitted or envisioned experiments for each error PDF set. Okay, and so then using these two inputs that can be readily available, you can quantify the strengths of constraints for individual experiments or given PDFs. You can examine agreement among the experiments. You could test for the sensitivity of processes that are not included in the global fit. And you can also compare constraints on the PDFs of the same flavor from different groups, because if you calculate this L2, well, this is, let's say, correlation of sensitivity, it has a standard definition. So therefore, for example, you could ask, what experiment provides the most important constraint, let's say, on the gluon PDF in a certain X range in the MSHT fit? And how is it different from the constraint on the gluon in the CT fit or CTEC JLab fit? Okay, so you can use this metrics, correlations and sensitivities, to answer these questions and to do these comparisons among the groups. And so they are very easy to calculate. So they really require you 15 minutes of the computer time in contrast of doing the fit that requires many hours of computer time. Okay, so then I have a number of slides showing how the sensitivities work. I'll probably skip them and you please read them. So they're quite straightforward. Maybe just show how, well, some examples. So one thing you can do is that, okay, so this is shown in this paper. You could take a PDF flavor of your interest, for example, the gluon, and plot it as a function of x on the horizontal axis. And then you can estimate the pull on the PDF at the given x value on the x-axis when we increase the PDF by 1 PDF uncertainty. Okay, so what's the idea here? So you would like to estimate what the observable is. For example, you would like to ask, is your cross section for, let's say, for a given experiment, is it sensitive to the gluon, let's say at x equal to 10 to the negative 2? Well, how will we estimate the sensitivity? We will vary the gluon up or down, and we ask, is the cross section of the chi-squared for our experiment change, right? So it's basically, it's kind of like a variation analysis. Okay, and so the sensitivity analysis allows you to calculate this variation very quickly. Okay, so basically I need to calculate the chi-squared for each error set, and then I plot the sensitivity for each value of x in the gluon. And so, for example, here what you will see is that, okay, so some experiments, so basically the curves here correspond to various ideas of the experiments. Like, okay, so some experiments, let's say, for example, here, well, let's say x equal to 0.5. So there is an experiment 5445, which is the CMS 8 TV jet production, that really would prefer to have a higher gluon at this range, because if we increase the gluon by 1 standard deviation, the chi-squared for these experiments goes down by 15 units. Okay, so therefore you can quite easily see what experiments pull the gluon in a given direction. So then now you could ask, well, what about the future experiments like the EIC or the LHEC? Well, you can do the same kind of sensitivity comparisons to them. And so like, for example, well, here is an example. You could ask, well, what will the EIC constrain? No, normally the EIC will, well, it's obvious it will constrain the quarks, especially the up quark and down quark. Maybe it will constrain U bar and D bar, so see this. But it also turns out it constrains the gluon. And not just at very large momentum fractions, but it also at smaller momentum fractions that are of interest for Higgs production. So the Higgs production will probe gluons at smaller typical X values that will be accessible at the EIC. But because the gluon is constrained by the momentum sample, so if you can measure the violation of the Bjorking scaling very precisely at the EIC, you will constrain the gluon for Higgs production at the LHC, okay? And so you can constrain it without using any nuclear targets, so it can be very clean measurement. And that's why, again, to emphasize one point is that it's very important to have the EIC running. It is concurrently with the high Lumi LHC for at least a part of the time, because we can come up with the synergies like this. We can constrain the gluon at the EIC and make predictions for the LHC. Well, you can do also other questions. So this is the other couple of plots very quickly. You can constrain Mellin moments very, 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 very powerfully at the EIC. And Mellin moments are computed in lattice QCD. So you have lots of synergy with lattice QCD. And you can also even try to constrain the quasi-PDF and pseudo-PDFs directly using the various techniques. And so basically what will happen is that EIC will really drive the comparison of lattice against phenomenological results. And so again, I have some plots, and you can even identify specific points in the EIC pseudo data, which will constrain, which will be providing very important constraints on the lattice QCD. All right, so then just to recap, so I think this is the last two slides, right? I hope, again, so I didn't cover many things, and thank you for allowing me to go a little bit over time, but I would like to convince you that global fits are really a very rich domain of phenomenology with impact on all sorts of measurements. Now you work with the most complex data sets, most precise calculations, but also there is this very interesting aspect of application of information theory to the precision fits. And that would require another lecture or two to discuss it, because these new ideas, well, they are very tightly related to these big questions. Can we use AI or ML for rigorous science? Okay, and so this is precisely the kind of sandbox which you can practically use to test various issues related to information theory. And this is just a list of things that you will have to study if you would like to properly understand statistics of multidimensional PDF fits. And you can ask me questions about it during the barbecue. And with this, I would like to thank you. And yes, thank you.